So we're now going to look at some problems in the book. We're going to turn to page 429 in the book and look at problems dealing with the z-test. And the first two problems we're going to look at in terms of doing the skills that we need to help develop future problems. So in problem number 35 on page 429, it says a test is made of h naught mu equals 50 versus h1, which is the alternative hypothesis. h1 is greater than 50. A sample size of n equals 75 is drawn, and the sample mean is 56, right? So x bar in this case is equal to 56. The population standard deviation is 20, so we'll put that down. And the sample size that we said was equal to 75. The first question is compute the test statistic. Well, since we know the population standard deviation, we will use the z-test. The z-test, here we go, is equal to x bar minus mu divided by the square root of n, sigma divided by the square root of n. And in this case, we just plug the numbers in. 56 minus mu, which is 50, divided by 20 square root of 75. Now when we do the calculation, we end up to getting 2.598, which is approximately equal to 2.6. Now, in order for us to answer B and C, we have to calculate a p-value. And so what we do is we go to the table, and when we go to the table, we look at the z value. Here the z value is 2.6, right? So we're looking at, here is 0, here is 2.6 on the table, and we're looking for this area here. Why? Because h1 says mu is greater than 50, right? So if mu is greater than 50, we're looking for this particular area here, right? So the way this works is we're looking at the probability that z is greater than 2.6. But from the table, we can't look at it that way. We've got to look at it in the opposite way. So our p-value is equal to 1 minus the probability that z is less than 2.6. And that's equal to 1 minus 0.9953. And this gives me a p-value of 0.0047. So in both cases, we have a p-value that's less than both 5% and also 1%. So we would reject both. Okay. Now normally we don't do these things by hand. We're going to use the z-test on our calculator under test. And when you do that, you'll just put in the various, under the stats part, you'll just put in the different pieces of information. Let's look at problem 37. Here we have a two-tailed test, right? Because the alternative is not equal to 130, right? When we compute our pieces of information, let's take a look at those. We have a sample mean is equal to 135. We have a population standard deviation is equal to 40, and we have n is equal to 63, right? It says compute the test statistic. Well, since we know the population standard deviation, we'll be using a z, so we'll go ahead and use a z. X bar minus mu divided by sigma over square root of n. That's how we start memorizing things. We keep writing the formula down. And now we put 135. Hold on just a second here. We put in 135 minus 130 divided by 40 square root of 63. When we do the calculation, I get 0.992. And now here's where things change a little bit for our value. For our values, when we have a two-tailed test, we have to consider both the top portion of the tail as well as the bottom portion of the tail. So how we calculate the p-value is we put this value, the z-value, on the z standard normal curve. Here's 0, and here is 0.99, and we'll also look at negative 0.99, and so we're looking at the areas both on either side of that value. And you say, well, that doesn't make sense, but that's the way it works as far as finding. So once we get a p-value, and we'll get the p-value over here, that's the easiest, we will double it. So our p-value under the two-tailed situation is equal to 2 times the value that we get for the probability that z is less than negative 0.99. Okay, and when we look that up on the table, we get, so this is going to be 2 times 1611, right? Which is approximately equal to, I think, 32%. Right? When we double it, we get 0.3222. Right? When we put these ideas into the calculator, we get something. We get a close p-value of 0.322. And we also get a close value of z, but of course there's rounding error when I do it by hand. Notice that this p-value, right, is bigger than these two values here, so we do not reject. Okay, since our p-value is greater than 0.05 or 0.01, we will not reject. So problem 53 on page 430 is an example of one of the problems you may have on your tests or certainly on any sort of project. So Here, older men are shorter than younger men. That's the question. According to the National Health Statistics Report, the mean height for men is 69.4 inches. In a sample of 300 men between the ages of 60 and 69, the sample mean was 69 inches. Public health officials wants to determine whether the height of older men are less than the mean height of the U.S. population. So in this case, we will state the hypothesis, right? So H naught mu is equal to 69.4, and H1 is mu is less than 69.4. I apologize for the my bad scribbling here, but it's hard to use it on this machine. Anyway, there's pieces of information we want to write down before we compute the test statistic. Here we found some information about X bar. X bar in this case was equal to 69 inches. There was N is equal to 300, right? And then in part B, it tells us the population standard deviation is 2.84, and that should be in inches, right? And it says compute the test statistic. So that's step 2, right? So Z is equal to X bar minus mu divided by sigma square root of N, right? And so we'll put in the values into the equation. 69 minus 69.4 divided by 2.84 divided by the square root of 300. When we do this by hand, right, we get a negative 2.4395 about, which is approximately negative 2.44, right? So now this is a one-tailed test. I have to find the p-value. So that's the next step, is to find the p-value. And to do that by hand, right, here is 0 and negative 2.44 is on this side. So we're looking for this area under the standard normal curve, right? So the p-value is equal to the probability that Z is less than negative 2.44, right? And in this case, we get 0.0073, right? And so now we're going to test it against that significant level. So since 0.0073 is less than 0.01, we reject H naught, right, and state that older men are generally shorter. And we could continue on. I don't have enough room, but we would want to say that older men are generally shorter than the U.S. population based upon this particular sample. Another sample may not give us the same piece of information, but at least anyway we have that kind of statement at the end. Also, typically, when we reject H naught, we do a confidence interval. We have to be careful on confidence interval for the alternative being less than a certain value, because the upper end of the confidence interval could just be touching the confidence interval. In this case, the CI, when we did it on the calculator, we got 68.6 to 69.42, and you'll notice that 69.4 is the upper end of this confidence interval. But remember, we're dealing with a one-tailed test, and so a two-tailed test, it would still be in the confidence interval, but it wouldn't be in the confidence interval given the fact that it's a one-tailed test. So our last problem, looking at the z-tests, we have some data, and so we have to put the data into the calculator, and we have to also check to see that indeed we're going to have a z-test if we have data. There are several things about this. First of all, it gives us a random sample of 16, so we have to check normality issues. So in this case, it's problem 60 on page 431. The mean GPA at a certain university is 2.8. The following table are GPAs for a random sample of 16 business students from the same university. So we enter this information, right? Into calculator to get X bar, or we can actually do all the statistics, right? We can do a z-test if we want to, which I'll compare the actual values. But when we enter this information in, I get an X bar equal to 2.91, right, from calculating stats. Sigma, in this case, is right here. It's 0.3, and N is equal to 16. Now, if you go to page 431, you'll see a box plot. It's there. It's normal, so we'll move on, right? And so now we can still do the test. It tells us that we can assume that the standard deviation is 0.3, and it says now we want to perform a test at 5%. So let's go ahead and do our test. So H naught is mu is equal to 2.8. H1 is, it says it differs, right? So if it differs, we're going to set up mu is not equal to 2.8, right? That's the step one, right? There's my step one. Step two is to do the z-test here. So z is equal to x bar minus mu divided by sigma square root of n. In this case, x bar is 2.91. I subtract out the 2.8. Sigma is 0.3 divided by the square root of 16, of course, which is 4. So we get an answer of approximately, if I round up, I get 1.47, right? And then this was step 2, this was step 1. Step 3 is to find p-value, right? And so we know how to do that, right? Let's go ahead and do that. Here's 0, we're on Z, right? And we have a 1.47 here. And we have a negative, because it's a two-tailed test, we have a 1.47 here. So I can find the p-value here by doubling it, right? Since it's a two-tailed test, the p-value is equal to 2 times the probability that Z is less than a negative 1.47, right? And that's equal to 2 times, when I found it on the table, I get 0.0708, right? And so my p-value is equal to 0.1416. So there's my p-value. If I do it on the calculator, right? Well, step 4. Okay. Step 4 is since 0.1416 is greater than 0.05, we do not reject, right? And so our conclusion is there's not enough evidence to conclude that the GPA for business students are any different than at the university level. I want to just go over a little bit. The Z-test will have a slightly different p-value. I got the information I got was, let's see if I can put it on here. I think the Z value I got on the computer. So the TI-83, I got a Z value is equal to 1.44, and the p-value was 0.1493. So there was rounding error, and so these were the values on the TI, and you may want to check that as well. That concludes our problems in 9.2. Hopefully I will get the T tests that we can look at as well. Thank you. Bye.